So I'm going to talk about machine learning quantum matter data. I just realized my title is not quite in sync with the abstract. Same kind of idea. So I want to talk about how we proposed and used machine learning tools to gain some insight from STM data, real space data, and also to learn information from the diffraction data. So what are the challenges in trying to deal with our quantum matter systems? I firmly believe that we've been doing data science before that language was invented, and just without knowing that what we do can be called data science, because we actually deal with a lot of challenges that have to do with big data and also noisy data, incomplete data. What do we want to do? We want to be able to learn how we go from some microscopic systems to emergent states, such as topological insulator, various topological states of matter, or high-T superconductivity. But trying to learn this emergence can be thought of as wanting to go from some complex reality of data to such as density of states measured as a function of position, voltage, temperature, doping, and other parameters, or scattering intensities measured over the Brillouin zone, reciprocal space, temperature, pressure, magnetic field, etc., or many-body wave functions. Our data sets are with the development in measurement techniques, or development in computing hardware, or development in the detector technology. Our data sets becoming larger and more complex. But even those who do make the measurements themselves cannot remember all the details of the data. And that's not what we call learning. What we want to do from these measurements, whether that's from the real data or synthetic data from simulation, what we want to do is to extract some simple principles. Because that's what we can pass on, that's what we can build on, that's what we can discuss and communicate. What are the simple principles? It could be some information about symmetry breaking, some ordering, or it could be something like topological invariant, which tells us whether we have a topological state or a trivial state. There's got to be a function that takes us from this kind of measurement data to some simple principles. That's what functions do. It maps from the space of your argument to the target space. But sometimes we know those functions, but oftentimes we don't. And especially as our space of data gets larger and more complex, it's harder and harder to figure out what those functions should be. Sometimes we have insight and our traditional knowledge that we've built on over the course of time that help us how to go from the complexity of the data to simple principles. And when we figure that out, it's very gratifying, especially if we can confirm that our approach for going from the complex data to simple principle was right, that validation can be obtained by being able to go from our simple principles and generate the reality of the data. But this can be difficult, especially when we deal with quantum many-body problems, and our wave function that we're trying to deal with is a complex big object. So what are the data-driven challenges that us who are studying quantum many-body systems face? There is the complexity of the many-body state. The Hilbert space is large, and our wave functions are functions in this enormous Hilbert space. This is just a way to capture complexity of many-body wave functions. This is wave function of 49 electrons visualized, and the way of visualizing here is to fix the position of all 48 electrons. So the green dots are electron positions, and let one electron move around. And every time there is a sign change in the total wave function, we change the color. And this boundary is called nodal surface. The geometry of nodal surface become complicated when we introduce interaction here, parameterized that way. But this is just a way of visualizing complexity of wave functions. But those who deal with wave functions through variational studies are well aware of this. Now, how about in real data? Tunneling density of states in 1960s were measured through these macroscopic tunnel junctions. And the resulting curve, because you have one measurement and one variable that you're changing, the bias voltage, was this simple curve. And we understand and love this curve, not only when it comes to the salient, very standing out features, such as the suppression of the density of state, suppression of the tunneling conductance, or this peak. We know this is gap opening, this is a coherence peak. Not only those, but also these little wiggles. We understand these little wiggles, and the reason why we say we understand it is because we actually can have a sophisticated model that can reproduce those features. And the model, it was put forth by these group of people studying strong coupling superconductivity. And these wiggles tell us that our understanding of BCA superconductivity is really largely correct because we can match this given the phonon information. But now stepping back, we can think of this from today's data science perspective as a kind of a generative model. Why is this a generative model? What generative models do is it gives us a way of making predictions. So this tells us if we make predictions, if we know the data points at some of these positions, we can actually use this curve to make predictions for other points where the measurement has not been yet made. And that's a prediction that we make that can be confirmed through experiment, and that's in the larger world called generative modeling. So this is a very sophisticated generative model with diagrammatics underneath and so on. The virtue of this model is that there is a very strong theoretical foundation, but one issue with the model from the generative modeling perspective is it's great when it works, but if it doesn't work, we only learn that, okay, we've got something that is not a BCS superconductor and we don't know how to go forward. In the measurement side, as we improved our measurement techniques, instead of having a macroscopic tunnel junction, now our colleagues have this kind of tunnel junction made by the vacuum itself. And as you move this tip around, you can make the measurement of the tunneling conductance as a function of position. Now your data volume has grown from a single curve to a curve per point of the measurement. So now that one axis we had when we were making the single curve was the bias voltage axis. And each of these points in these pixels, there are a lot of points where these measurements are being made, and for each of them there is a curve. And what it's showing as we look at the energy slice is that, well, there is a lot of variation in space. And some of the variation would be simply a result of impurity, but some of the variation is a collective phenomena. But we don't have any hope in trying to fit this with a kind of analytic model like the model that I showed you earlier. The reciprocal space, this is 3 by 3 by 3 Brillouin zones, data we got from our colleague at CHESS. It's a high energy synchrotron source at Cornell. And this is a diffuse scattering data. Until I saw this data, I thought X-ray is about giving me the location of the atoms. And if I think about simple systems, not like DNA crystal, but solid state systems, I just figure out the location of atoms, give me the lattice constant, and if I know what the atoms are, that's about it. That's the Bragg peak. But all this intensity that's spread out, these are diffuse scattering, and there's a lot of information in it. But trying to figure out where the interesting information is really the problem of needle in haystack. So there's a lot of large volume of data space, and there will be some points where interesting action is happening, and we don't know where those are until we can find them. And the problem is the current way of analyzing this data is largely done through human inspection, and we cannot visualize 3D when you have scatter of data. We can visualize 2D. So what people have to do is make a slice through this haystack or the diffraction data, and see whether you can identify a feature. If you do, good in one shot, but if you don't succeed in the first try, then you'll try making another slice and another slice. It's a very time-consuming process. And not only that we have such haystack at each point in parameter space, we change temperature, we change pressure, doping, etc., and we have a lot of these variables. What my group have been focusing on facing these issues that are data-driven challenges is to try to get new insight through synergy. That is, this is not so unique in a way about what my group is doing anymore. In different fields, people are discovering more and more. In order to be able to use the developments in data science tools or machine learning tools in a problem of your interest, you have to really seek the synergy between what's called domain knowledge and the machine learning tools. So my domain knowledge is this, that I know what topological defect means, I know what RG means, I know what symmetry breaking means, and I know what is the insight that we're after. So what we have been doing is largely looking at what computer scientists will call synthetic data, that's simulated data, as well as real data from experiment. And let me just give you a quick preview of some of the things we are doing, but then I will spend most of the talk discussing the studies of real data using both supervised learning as well as unsupervised learning. So we actually done quite a bit of work, and we're still working on various ways of looking at the synthetic data. And this was a paper that I worked in collaboration with my former postdoc, Frank E. Zhang. He's now a faculty member at Peking University, starting his own group. What we figured out here is that this quantum loop topography was what we've came up with as a pre-processing step. And this kind of pre-processing or data preparation is where the domain knowledge can enter. Knowing what kind of input would have the information about topological invariance, in this case Chern number, we were able to detect the quantum phase transition associated with topological insulator, the transition between topological insulator and the trivial insulator. And we've now built on that to study Z2 topological insulator, Z2 spin liquid, and disordered quantum Hall systems. Another thing that we've been doing is to learn transport information from imaginary time data. Now, if you want to learn about transport, that is to calculate the optical conductivity from imaginary time data, what one tries to do is to do, say, analytic continuation. But analytic continuation is an ill-conditioned problem, and there are various challenges. So the idea was, can we just learn the information that is relevant for transport in the imaginary time data, Matsubarra frequency Green's functions directly? So here what we did was, again, using quantum loop topography that is capturing the relevant information that would enter conductivity in a simple setting. And using that data, we were able to get the neural network to learn the difference between a superconducting state and a metallic state, and sort of crossing over through a fluctuation-rich region. And this region over which we are transitioning from the metallic state to the superconducting state was actually consistent with other more established ways of detecting superconducting fluctuation. And we're now extending this to study of non-Fermi liquids. In this work, we were able to learn out of equilibrium phases, many-body localized phases, and actually distinguish two different types of many-body localized phases, and this was featured in various outlets. So now, in the rest of my talk, I want to talk about how we try to learn, gain insight from complex reality of data. And I'm going to discuss two different approaches. One is using supervised learning, and the other is using unsupervised learning. And these are not only that there's a difference between whether you supervise or unsupervised, but it's just kind of different mode of studying. In supervised learning, you're trying to learn the function, and that function that connects you from the data to some input, some insight that you're after. And you're training your model, such as neural network, to learn to represent a function. And once you learn the function, once you're convinced that your neural network learned the right function, then you fix the parameter, and your neural network is a function representation. And you feed in your input, and it will give you the output. That's how the functions work. In the unsupervised learning, you either do clustering or you do generative modeling, and it's a very different mode of learning. So I'll come to that when we discuss unsupervised learning, but I want to first start with discussing supervised learning. So here, what we're trying to do is we want to test different hypotheses we have about experimental data. Typical mode of how the experimental group works is that when they plan experiment, they have some hypothesis they want to test, some theoretical hypothesis. And maybe there are multiple hypotheses, some put forth by their colleague at Flatiron, another put forth by their colleague at NYU. And if the two are different, you want to know which one is closer to reality. That's a hypothesis test we do. So what do you do when you do the measurement? You have your data. Your data is typically not going to look like either of those ideal hypotheses, because real life is always much more complicated. Then you have your data that doesn't look exactly like either of the hypotheses, and you want to test which one is a better representation of the data. That's the hypothesis testing. So we want to do this hypothesis testing by using a neural network that's been supervised by the label data where we know what the right approach is. So in order to talk about how this supervised machine learning hypothesis testing works, I need to tell you how we supervise the neural network to learn. So the way I think about it, the reason really I think I was able to enter this field of machine learning is because of my experience as a mother. I really totally credit my experience as a mother to boldly jumping into this field. Those people who know me were very surprised that I'm doing this, because I'm not known to be a computational person. Not very good coder anyway, still. But my students are good. So I just need to know the strategy, and I know that really well because I'm a mother. So how does that enter? The way we train the neural network through supervision and feedback is very much like how we try to train kids. What we try to do is we try to train kids to make the right decision. We try to train the neural network to make the right decision. And decision making is a function that takes the input of your situation you're in and coming out to the decision. And your decisions are often, could be a set of choice among a finite number of options. So it's a multiple choice. So you're trying to go from your data to your multiple choice outcome, and that function is what you're trying to learn. So what are the inputs that one takes when you're in this situation? The inputs are going to be how long has the food been on the floor? Is mom watching? Because the mom is a bad cop in the family, in my family at least. And how sweet is it? How green is it? These are the kind of inputs that my kids will take. And there will be a decision, output. Output is whether to pick it up and eat it or let it be. Okay? Multiple choice with two choices here. And what's happening in their brain? I have no way of knowing, but I can guess. A neural network is a very simple-minded kind of model that's not verified, but model based on one idea. The idea is that we have to take the input and come to a decision. And there is this thing called firing. Neurons are connected through synapses, and it takes some threshold amount of current before it fires. So we incorporate that. So there are different neurons. This is N1, one neuron, and my son knows the name. I think it's called amygdala or something. Reptile part, the lower part of the brain. And there are other parts of the brain, the upper part of the brain, mammal part of the brain. So different neurons, each of these different neurons, I've labeled with N1 and 2 because I'm forming a vector of it. And they will be connected. They will take this input, each neuron in the fully connected V4 neural network takes input from all the input vector. I've labeled my input information with subscripts because this is also a vector. So I take this vector input and I put different weights. Different neurons will put different weights for different input. And this is a function of the input as well as the neuron itself. So I have this weight matrix because I've got two indices and I've got the bias. And once each of the input is processed by each of the neurons, this information will be collected again through this weight distribution, and you come to a decision. So then the way we train, the way I train my kids is not being able to go into their brain and change these weights and biases. I wish I could, but I can't. So instead what I do is I give them feedback. When they make the right decision, I tell them that's a good thing to do. If they make the wrong decision, I tell them that's not the right thing to do. And we do the same thing with the neural network. We train them through giving feedback. But now if we step back and look at what the neural network is, we can recognize this is just a representation of function. And now because there is another firing function here, there should be one more sigma here. But this is a function that you're figuring out. And once you've learned the weights and biases, you have a fixed function representation. And the training through feedback is when you have a label data set that you are using for training, that is their life experience before they go to college. That will be the label training set. Each time I tell them this is right, this is wrong. And hopefully they've been trained enough. Once they are trained enough, they will be able to make the right decision on their own. And the feedback giving mechanism is right here. So this is what will be the output that's coming out of the neural network given the input in the current state of the neural network. And this is a label, whether it was something that's okay to pick it up and eat, or it is not. And what you're trying to do is minimize this cost function. There are other measures, but typically this is looking at the distance between the designated known label and what comes out of the neural network. And you adjust the weights and biases, that you adjust the functions themselves through this stochastic gradient descent until this cost function has been minimized. So how do we use this approach to look at the STM data set, and what do we try to learn? So here, the hypothesis testing that we're trying to do for this kind of STM data set, this is STM data set taken from a pseudogap state of high TC superconductor. And we want to be able to say whether one should approach this from real space, very local perspective, or should we approach it from K-space, the itinerant perspective. And what we try to make, the idea is that there should be a function that takes us from this data, which I have even different energy dependence, to this output. But I don't know how to write that function. And I would like to be able to just figure out what the right function is and make use of it. So this work was done in collaboration with these colleagues, Frank, who's I mentioned earlier, and Andre Mezaros, who's now a staff scientist at CNRS, and Kazu Fujita, who did all the measurements, Isan, at San Jose State University. We started working together at the initial stage of designing the neural network, and Seamus, my longtime collaborator, who's overseeing the STM measurement. So what is the question that we're trying to answer? One of the mysteries of high TC superconductivity is that its phase diagram is complex. And this complexity is in contrast to the conventional simple superconductors, elemental superconductors. For elemental superconductors such as mercury, this is the original data plotted, there was just a simple one-dimensional phase space, that's just a temperature. Only parameter that you tune, you have a pure metal above transition temperature, and you have a superconductor below transition temperature. What came with the advancement of high TC rates, which has been now demonstrated to be also occurring in other newer compounds such as iron-based superconductors, is that phase diagram is much more complex. And there are phases that we know, such as antiferromagnet and superconductor, but there are phases that come with this kind of name, pseudogap and strange metal. These are not very informative names. which kind of reveals the degree of our lack of understanding. There have been a lot of progress in various measurements that are indicating that there seems to be some sort of symmetry breaking that are nevertheless kind of short range than glassy. And in reciprocal space, they show up through a broad peak. In real space, it shows up through this kind of pattern formation. And these patterns that you see, there is some periodicity that is not exactly that of the lattice constant. So these green crosses are locating where the atoms are. So these patterns that are showing up is not the pattern of the atoms themselves, it's the collective behavior of electrons. And one would like to be able to learn these local motifs. The question that we wanted to address is what is the right way to think about the origin of this pattern formation? Should we start from strong coupling real space perspective or weak coupling K-space perspective? And should they be viewed as disordered version of checkerboard or disordered version of stripe? The strong coupling perspective starts from antiferromagnetic order at monoinsulator, and you say, well, I try to dope in holes, my holes carry spin, and it would have to disrupt this antiferromagnetic arrangement among copper spins by going into one of the oxygen sites in between. And because my oxygen, the whole spin also wants to be antiferromagnetically aligned with copper, it's going to frustrate the copper-copper antiferromagnetic desire. So if you're frustrating this interaction, with the copper alone, this is what they want to do, but now you have to form this kind of domain wall, and it would be energetically favorable to align those holes together to minimize the penalty of frustration. And this kind of perspectives led to saying that any periodicity that you will form result of these strong coupling interactions is going to be commensurate with the lattice, because you're trying to really mitigate the effects that were happening at the lattice scale. And because there is a advantage in having some delocalized holes along one direction, this will favor unidirectional modulation. The weak coupling perspective is to say, let's start from the itinerant, the free fermion side, that is the band structure. And if my band structure have nesting, that nesting is going to drive this pattern formation. And in this perspective, because there is nothing really the lattice scale is entering in deciding what the nesting vector is, this is just a matter of your filling, the size of the Fermi surface. So this wave vector is going to be typically incommensurate, and you expect checkerboard because there is this as well as that, and you want to nest as much as possible. Now, conventional approach to looking at these kind of spatial modulational pattern is to try to do Fourier transform. But if you just do Fourier transform, that does not compress the amount of information you have. Remember, we are trying to go from large complex information to a few decisions at the end. Fourier transform is a linear transformation. It does not change the amount of information in it. It's just a change of basis. So if your new basis is good, where you have lots of information really showing up in some restricted space in the Fourier space, then what you can do further after Fourier transforming is to compress the entire Fourier transform down to just the peak location of the line cut. And that's what is typically done in analyzing this kind of data set. So let's look at this data and let's try to Fourier transform. If you Fourier transform, it's got to be larger space to get this much intensities. But if you Fourier transform and just look at the intensities, you get this. Now, this is color plotted to reflect the phase. Now, if I make a line cut, because I cannot read this very well, if I make a line cut, this is the x direction and this is the y direction. And for technical reasons, they always make the measurements in this 45-degree angle rotated frame. So this is the x direction, and this is y direction, so I can make a line cut and look at what the line cut gives me. This is the intensity along this red line cut. It's very jagged because there is a lot of local things happening in the system, and features are broad. So now if I'm interested in keeping track of what is the representative Q associated with this modulation, because we want to be able to just remember one number instead of a whole set of numbers, I am kind of torn looking at this thing, like where should I place the peak location? Nevertheless, what people have been doing is you take this kind of data and you fit some sort of broad peak shape, that would be Lorentzian or Gaussian, typically Lorentzian, and say that the centroid of that Lorentzian is representative of my data. But that approach, and then throwing out the rest of the reciprocal space, is not a sound regression scheme, is our position. And actually, people have studied trying to answer the questions that we are after. Is it real space versus K-space? Is it checkerboard or stripe? In these papers, this is from Stanford group, this is from Harvard group in 2006, and they both declared defeat within this kind of manual schemes. They failed their own blind test. What it means is that they will generate the data, they will simulate data to have this level of the level of short rangeness, level of disorder that is seen in the system. A student will generate them starting from one hypothesis and another and give it to their advisor, see if they can guess where it started from. And people couldn't guess where it came from by looking at the final data, which had all the real data like noise and disorder. So what we're proposing is to use neural network for that hypothesis testing. What we do is we have our label data set here is the idealized hypothesis, where we can just write down analytical expression for what the dominant pattern is, and then we will diversify the training set which is necessary for training through noise and fluctuation and disorder that's added. And in this step, training data set generation, our domain knowledge enters. Our knowledge of how to represent the charge modulation, our knowledge of what kind of disorder there can be, that there is amplitude disorder and phase disorder, those things all enter in that stage. And then we set up a neural network and we train it, whether it can distinguish different hypotheses, and we look at different outcomes. So how did our domain knowledge enter in training set generation? So this training set was generated with this kind of formula, where we have phase, noise, represented by these two phase terms that are position dependent, and we have amplitude noise, and there will be form factor that would be informed by the measurement. And the phase disorder would not only have smooth varying phase, but would also have topological defects incorporated. And the different hypotheses that we wanted to test had to do with what is the simplest way of capturing the data set if we were to try to capture it through a single modulation periodicity. So these are different periodicities that we chose as a model statement. And these numbers look kind of funny, but they were chosen actually in the reciprocal space to give you the weight around where you see the large weight in the free space. And one thing you can notice in looking at our 4 different categories that we try to discriminate against each other is that one category, category 2, is commensurate, and the other 3 were incommensurate. So now we're going to look at the doping dependence. So now the data set is taken from these different positions in this range over here, and this is at the lowest doping. This is the real space data, and this is its Fourier transform. It looks pretty broad, and this is the outcome of the neural network. And these are different representative periodicities, and what's obvious is that the category 2 associated with period 4 is showing the most dominant weight. Now let's move up in doping. Now we moved up here, and again we see that category 2 is much more dominant than the other. Now the difference between red bar and the yellow bar is our training set was unidirectional modulation. So what we do is we give the data set in one orientation, and then we rotate it 90 degrees, giving another orientation. And neural networks assessment is now represented by red histogram for giving in this orientation and yellow histogram for giving in that orientation. Another thing you can notice here is that the period 4, category 2 is clearly most dominant, but only when you present it in X orientation. So that tells us that X orientation and Y orientation are actually quite different. Now I further move up in doping. This resolution isn't very good, but you see that same kind of trend continuing. But now I approach near optimal doping of 20%, and all different categories are neck to neck. You cannot really distinguish them. And that's really because the modulation information is kind of lost at this point. Now, what about energy dependence? I said that one of the challenges is that we have this lot of energy dependencies as a function of position. At some energy scale, we start to see this category 2 kind of pick up, and it kind of continues on as we go up in the energy scale. And this energy scale at which we start to see this category 2 pick up is a pseudo-gap energy scale. This is looking at all the energies. And by looking at the responses of different output neurons associated with different categories, we can really see that this category 2 really picks up at this energy scale and stays to be dominant. So based on these analyses, we concluded that looking at this data, starting with 2 different hypotheses, let's say these are sort of a pseudo-hypothesis because actual choices we were giving to the neural network was not exactly this versus that, but we had 3 categories associated with different wave vectors that are incommensurate, and 1 category associated with a commensurate density wave. And our conclusion is that across the entire underdoped regime, it was commensurate, and C4 breaking, that is stripe, is a more dominant pattern, the motif that the neural network was able to recognize. Now, so this was it was an exciting result to have, especially because in the very underdoped regime, this previous mode of analysis was giving the dominant modulation wave vector to be very different from period 4, and the guiding sort of dominant wave vector or the periodicity to be the function of doping. What we are finding is that it's universally well captured by period 4. This is really, in a way, more objective way of quantifying and presenting what our eyes see. Our eyes are very sensitive to motifs, and our eyes have been seeing these motifs for over 12 years. But when we communicate what our eyes sees, it's conflated with our bias, our personal view, etc. And using neural network, we were able to kind of capture those motifs that we were seeing. Now, as I promised earlier, I want to start discussing an unsupervised machine learning mode of looking for the needle in the haystack. If the supervised machine learning was about trying to learn a function, using a basis to represent the function and learn what the function is, in unsupervised machine learning, when you do generative modeling, what you're assuming is that there is going to be a distribution of functions that can capture your data, and you're going to try to learn the distribution of functions and use that to gain information. And this work was done in collaboration with my 2 amazing students, Jordan Vanderlee and Mike Matty, and together with computer science colleagues Killian Weinberger and Andrew Wilson and their student Jeff, and experimental data was presented to us by Jacob Roth at Chess. So now, looking at this reciprocal space data, what people have been doing is they will put a slice. For instance, if we put a slice where you see this flat region, what you see is this kind of distribution. And if you chose the right slice to make, you would be able to say, well, there are intensities here and there are these broad intensities. But if I didn't choose the right slice, I would miss out some of these intensities, and especially the ones that we care are these two. So what does the diffraction measurement measure? Well, it measures these intensities are the free amplitude of the structure factor. And if we have a density wave as some wave vector q, that's going to give us order parameter showing up here with complex order parameter at that particular periodicity. So finding q is finding the density wave. If I find a right q in that whole space of reciprocal space, and measuring the intensity at that q will give me the order parameter. So now let's look at this, entire data set. If you look at how intensities change as a function of temperature at each of these points, you get a curve like this. This is a collection of a lot of curves. There was about 100 gigabytes of data here. We're looking at all the curves. And there are some things that are standing out, jumping out. So you see this large intensities, they stand out. Well, they are important things. Those are Bragg peaks. They just tell me about the lattice constant. And this is what we use to normalize the temperature to sort of subtract out the noise. So that's not a meaningful feature to look at. Then where is all this diffuse scattering data? Where is some collective phenomena that I'm after? That's not about the location of atoms. They are all down here. So let me blow that up. Looks like this. Somewhere in this temperature trajectory is that order parameter behavior. There's a lot of noise, and it's hard to figure out where in this haystack is my needle that I'm after, the modulation wave vector. So the mission is to accelerate discovery by sorting through this large volume of data. And instead of spending weeks and months of inspection by eye, we want to be able to find where the exciting action is happening in reciprocal space in the measurement timescale. And the strategy that we're using is to discover the model that is the generative modeling side, and at the same time classify or cluster different regions in the reciprocal space as where exciting action is happening versus where it's just about the atoms. So the prototype system we're studying here is 1T titanium diselenide. It's a well-established charge density wave system that's been around for a long time, but it's not like there haven't been some new developments. Recently, there was observation of possible chiral order. There's discussion of exciton condensate, and if you intercalate with copper, you get superconductivity. But we chose this data because we know everything about this data, so this would be a good place to benchmark the new method we're trying to develop. So what is the generative model? The traditional generative model would be, for instance, starting from this kind of data set. All of you are educated enough to look at this and recognize what it is. All measurements are always done in discrete space, right? You do measurements at discrete temperatures. So this is what the measurement looks like. But all of you, the moment I showed this plot, were drawing this curve and recognizing the mean field exponent, and you know this is a mean field order parameter plot. But pretend you didn't, okay? What we've just done is a generative model that's well established, well understood generative model, but it took humanity some time to come up with this model. What we have is using these data points where the temperature measurements happen and where the order parameter has been measured. It could be, say, magnetization at some discrete points. Those were put into our brain, and what came out is the predictive model that is based on mean field theory. What does mean field theory afford you? It tells you what to expect for the measurements that you haven't yet made, given the measurements you have made. When you use your generative model, that's the mean field theory, all you're trying to figure out is turning this volume of training data. It doesn't look like a lot, but compared to two numbers, it's still a lot more. So you take this volume of training data or measured data, regress it down to two numbers, and once you have those two numbers in your model, you can make predictions for the measurements that have not been made yet. That's how generative models work.
But I'm sorry, may I ask?
Mm-hmm.
As you presented it,
mm-hmm.
this problem appears to be curve fitting and interpolation from the points.
Mm-hmm.
So what's the difference? I mean,
yes, it is curve fitting, right? So if we didn't know mean field theory, if God didn't give us Landau, we would be doing just blind curve fitting, right? So what if the model was unknown, or if the mean field theory didn't work? What are we going to do? We will have to do some sort of curve fitting, and that's all generative models are kind of curve fitting. But then what are we doing better than the curve fitting that you've been doing all along? Well, I know how to fit linear, not even a curve. I know how to do polynomial fit. That's kind of where my knowledge stops. What I'm trying to say is that when we just do curve fitting, our options, the choices of the functions that we're using can be very restrictive. And neither linear curve nor the polynomial curve will capture the training data that I've shown you. So instead of just trying to fit a function by identifying the numbers within the restricted model that I'm working with, that will be curve fitting. In generative modeling, especially the Gaussian processes that I'm going to use, what we try to do is to try to discover the distribution of functions and say that my data could be viewed as drawn from the distribution of functions. And then what I'm getting is not only a fit function, but I'm opening my schemes to be very diverse and flexible. And I'm also going to learn what is the likelihood of my choice being the right function. That is, I'm getting the variance. Having variance is advantage of generative models such as Gaussian processes or generally Bayesian methods. So in Gaussian processes, you assume a function that you're trying to learn is drawn from a Gaussian probability distribution over function space. So if I draw my function from that's Gaussian distributed to have a mean of 0 and a variance of, say, 2, a random function I will pick will look like this. But as I draw more and more and more functions, I will be getting the distribution. So if we do the Gaussian process regression on this data, pretending we didn't have Landau, this is what we can get. So here, this red dashed line is the mean function, but we've learned the distribution. So what this gray is telling us is the variance or confidence that I have on this function. This is inferior. I am very clear about this. This is inferior to Landau. Okay? But if we don't have an analytical model, if we don't have a model that's given coming from some principled approach, you're not going to capture this function through a polynomial fit. You're not going to capture this through a linear fit. But you can discover what kind of function captures this data set best, and what is the degree of uncertainty that you have at different spaces, different positions in my phase space by doing Gaussian process regression. So this tells me that if I want to make a prediction at new point where there is no measurement, and I make the prediction to be right at this point in the dashed line, I would have this degree of uncertainty at that point. If I make guess right here, I would have this degree of uncertainty. When there are large spacing between the data points, I have this degree of uncertainty, but I would also have a prediction.
So again, may I push you on
Yep.
this a little
Yep.
bit? So I could say exactly the same things about just doing a spline fit to the points that you have, and my uncertainty would be smaller. In particular, in this case, because my function is essentially a scalar function of one scalar variable. And indeed, you know, that once I put error bars on the points and get some. So it seems to me that, and this is presumably where you're going, but that it seems to me that this sort of approach will have advantages when you have a function which is defined in a much higher dimensional space. That
Absolutely.
Both that it has arguments that
Right.
are drawn from a much higher dimensional
Absolutely.
space, and that the function itself lives in the much higher dimensional
Absolutely.
space.
Yeah.
And that therefore the crucial questions about each of these things are essentially how does it scale with the increase in dimension of the function I'm trying to represent and the arguments.
Right.
Is that?
Yes, that's absolutely right. But there's a little bit more to that. When I know spline fit is going to do well, I will do spline fit. When I know, by looking at the structure of the data, when I know linear fit is going to be reasonable, I'll do that linear fit, right? So that involves my intellectual decision and my experience and me staring at the data to make that decision. But if my structure of the data is so big that I cannot stare at it and make that decision, I want to be open-minded. So this allows you to be open-minded about the scheme of fitting. And actually, I'm trying to do, let me just finish. I'm trying to do more than fitting. I'm actually not interested in fitting itself. I'm interested in sorting through my haystack of reciprocal space temperature trajectories and sorting it into the reciprocal space points that are giving me something exciting happening and points that are not giving me exciting happening. And I'm going to do that sorting not by doing forward modeling, but by observing different trends as a function of temperature. And that's how I use the model.
Yeah, I mean, again, is there a literature on the question of how you define the function space? And particularly as you go to these larger dimensional sets where this approach presumably has very serious advantages.
Right.
How does what you get out depend on how you choose to define the function space?
Right. So, this is all, I think this fit under the larger umbrella of a Bayesian approach. But what I'm particularly going to focus on is what is quite often used, that's called Gaussian processes. And the advantage of Gaussian processes is that there are various stages at which you have linear transformation. And Gaussian retains its structure when you do go through these linear transformations. So it allows you to do something that is very principled and well-defined throughout. And it is pretty flexible. And in some cases, you can show that Gaussian processes and infinitely large hidden layer neural network amount to the same thing. That is, we know the central limit theorem. You know, if your data volume gets larger and larger, you will approach some sort of Gaussian in some space. So that's what Gaussian process is, and you can learn up about Gaussian processes. And I'm choosing the order parameter not because that's what you should do when you see the data like that. You should just use Landau if you see data like that. That's what your education was about. But because it's something that's familiar and I can visualize. So I want to find the goal is to find the conditional probability. Going back to this example. What is the conditional probability? What do I have? What I have is a measured data. So I have points at which the measurement has taken that I'm going to represent with x. That's the t1 to tn, the n where the measurements have been taken. And I know the value of the function as measured at those points, at delta 1 to delta m. Given this knowledge, I want to be able to make a prediction for the data point that hasn't been measured yet. And I want to be open-minded about the fact that my knowledge, my guess is not going to be perfect. So I want to have a probability of conditional probability given the knowledge what is the likelihood of my new measurement that I haven't measured yet at this point in t, giving me different possible values on this axis. So if I do make a measurement at this point in temperature, I will find some value, but I want to predict that with the knowledge of uncertainty. And I want to be able to say that, well, the likelihood of the measurement coming out to be this value is some probability 0.95, and measurement coming out to be this value will be 0.000000000, a lot of more zeros, one. So what is going to be the new unmeasured data? And that's what's called test data in Gaussian processes. And what you're trying to figure out is what is the probability given your knowledge. And in Gaussian process, you actually assume that you know this conditional probability that is given the test data, measurement points t's, and where you want to measure the training data and test data measurement points, what the outcome is going to be given by some normal distribution with kernels and some means. And given that assumption, so this is kind of a model, but it's quite versatile because we're modeling in the function space, a distribution in the function space. We're going to integrate out the trained data y, and if we integrate out this, we will get the conditional probability we are after. It's still going to be a normal distribution because of the property of Gaussian. That's the advantage of using Gaussian process. And what we're going to find is what is the mean and what is the variance. And it is known once I determine the kernel, I can figure out this mean. And so the whole thing boils down to figuring out what the kernel is and inverting this big matrix. And as my dimension gets larger and larger, I will have to invert larger and larger matrices. So I win the versatility of the representation, but I have a cost. Nothing comes for free. I have to invert larger and larger matrices. And it's really in figuring out shortcuts to inverting these large matrices where interaction with my computer science colleagues are really helping because they have very fast algorithm for doing this Gaussian process modeling. So that was Gaussian process, which just looks like fitting, some glorified version of fitting. But what we're doing is actually Gaussian process mixture model where we're doing clustering. So a single Gaussian process gives us this conditional probability as GP or normal distribution with a mean and a variance. And now if we have multiple Gaussian processes that is present in the data, what we are trying to learn is that, okay, if I have a data point, it's likely going to belong to one of the clusters, K clusters running from K, 1 to K, and each are going to be represented by this Gaussian process. And this is called Gaussian process mixture model. And this allows us to sort through the data and cluster different regions. And what we are really trying to learn is this weights and the clustering. So let's go back to this data set, which was taken from this reciprocal space. And what we do is we go through several steps. First, we separate out the background by removing small mean and variance, averaging over the temperature dependence. And that reduces our volume to be studied to this space. And then we separate out neighbors of the Bragg peak. And now these are the regions that are neighboring Bragg peak that leaves us this set of points. And now we do the Gaussian process clustering on these set of curves. Okay. Now when we use the measured data as the training data, and test data is different temperature points where the measurements does not exist, it's going to give us the prediction. But moreover, we get the clustering result. So taking this mess, the result of clustering gave us these set of red curves and these set of black curves. And the set of red curves are showing this behavior. Now, there is this additional kink that we are finding, which might be related to the chiral ordering. And this is the transition temperature. and you see one cluster, although there is this large variation, belong to sort of an order parameter-like behavior, and there is another cluster that is a background. And now if we track all the reciprocal space points that gave us this order parameter-like behavior, we discovered where the charge density wave is. So taking this, we found if we take the right cut, we'll find the CDW peak associated with pi and pi 0.
So what are all the other things on the left? So there are lots of spots.
Oh.
And then you said you took the right cut and you found pi and
Oh,
pi 0.
yes. So sorry.
Space, right?
Yes. So these are a lot of reciprocal space points. This is a 1, 2, 3, 4, 5, 6. I think we had 7 by 7 by 7 brilliant, 7 cubed.
It's multiple
brilliant zones. Right.
Okay.
So we take multiple brilliant zone data and process it all together. And here I'm showing you only one brilliant zone. But we can study correlation from brilliant zone to brilliant zone in this way as well.
But may I understand, is this, I mean, the sort of the low-tech algorithm is I sit in one brilliant zone, I have a large number of points, let's say, 10 million points, 10 million K points.
Right.
For each K point, I interrogate the temperature dependence.
Yep.
And then I wish to distinguish ones that have a boring, basically flat temperature dependence
This is that, yeah.
from ones
Yeah.
that, wait, so I could just make a list.
Yeah.
And I could see temperature dependence, not temperature dependent, and then I could ask, what's the common property, if any, of the ones that have a substantial temperature dependence, or a similar temperature dependence? So this is an efficient way of doing that.
Absolutely.
Okay.
Right. So this is an efficient way of doing that. Because if I look at within one brilliant zone, right, there is quite a bit of variation in intensities within a given brilliant zone. So if I try to keep track of this, if I had just 3 curves to stare at, I can do it. I think I can maybe do 50. But this is just a lot more. And just staring at this is very labor intensive. And if there is more than one thing going on, 3, 4 different things going on, and if I want to study how different brilliant zones are behaving and so on. So all this is so far done manually, and therefore, because it's time consuming, the way these measurements are done is people do measurements at the synchrotron light source for a week. They have a week of beam time. They go back home and spend next 6 months to a year analyzing data. And we would like this to be done right at the beam line while they're making the measurement. So they make one measurement one day. They find something, someplace that's interesting. The next day, they go into the region where it's interesting and study that further. And this is really about trying to accelerate that process. So, yeah. Let's see, actually. Yeah, so we start from this data set, and we go through some ways of sorting that's done automated in the algorithm, but sort of sorting out data in this large-scale background because the Bragg peak or anywhere near Bragg peak has about 10 to 100,000 times higher intensity compared to any other point in reciprocal space. And then you cluster that to discover the charge density wave peak in this case. And in this particular example, this is, we think of it as a guinea pig where we are using this data set to develop the algorithm. And the reason why guinea pig has to be a simple thing is because we want to make sure our algorithm is robust and it does the sensible thing where we know it. But what we are really after is being able to use this kind of approach to accelerate discovery or study data sets in a comprehensive way. All the complex data set, when we rely on human inspection, it has to be compared against the models that we devised, and it's limited to the graduate student lifetime that we can pay. So many of all these reciprocal space data sets are often investigated within some limited scope, and after about a year of mining it this way or that way, without having looked at the entire data set, it's often looked at by about 10%. And the rest of the data set has not been really looked at, but because you cannot afford to study the same data set for 4 or 5 years, people will move on. And what we are proposing is to use this unsupervised machine learning and clustering to accelerate the discovery. And so what I talked about today is using supervised machine learning to do the hypothesis testing and learn the order parameter symmetry, and unsupervised machine learning to do clustering in real reciprocal space. But really, the journey has just begun, and I think there are a lot of other ways that machine learning can help us learn more from the data that we belabor to take and detect. Thank you for your attention.
So we didn't have so many questions during the talk, so now's the time. Come on.
Yes.
So you had mentioned connecting transport from imaginary time
Yes.
information
Right.
In the connection of maximum entropy. Would you expand on that a little bit?
Yes. So we haven't, let me see now. I have some slides, I think. I'm just trying to get to some slides I think I have, which might help. Is this? Yeah, but you never have the right slide.
Machine learning.
Yeah, I need to do machine learning on my slides. Yeah. Search through the database of slides. So we didn't do any maximum entropy. So what we're doing here is, whichever way of doing analytic continuation, you start from the imaginary time data. And analytic continuation is a way of trying to go from the imaginary time data to, let's say, sigma as a function of omega, right? You're trying to learn the function that connects you from the imaginary time data to the conductivity that you're after. But if there is a function that exists, and perhaps maximum entropy method will do it, but what if I don't necessarily want to know the function so that I can be quantitative, but if I just want to figure out, is it possible to learn up, do the data mining on that imaginary time data, not relying on analytic continuation? Because surely you are not generating more information when you do analytic continuation. The information is already there. So the idea was to start from, do you have boards, like something to write on?
Yeah, we have it's back there.
Okay, what can I do? What can I do?
Well, maybe, may I make a suggestion if
Yeah.
you want to write on the board? Maybe we can just defer this part
Yeah.
of the discussion to out
Yeah.
there where there's a board.
Yeah, because we have
Yeah.
nice space over there, with, also with cookies and coffee.
Yeah, we
You'll
can do
be
that.
able
Or
to explain that on the board.
yeah, I didn't even bring my. Yes, let me just use words and see how far I can go with it. I didn't bring my tablet. I could just lift it up my tablet. So you have your 2-point functions, right? You can evaluate 2-point functions if you do any Monte Carlo.
Mm-hmm.
We evaluate 2-point functions at a given Monte Carlo instance. So if I want to actually get the 2-point function, Ci dagger Cj, expectation value, that expectation value part requires doing a lot of Monte Carlo updates. But we're not going to do the updates because each of those updates have the noise that gets averaged over when I average over a lot of updates. But I am okay with having noise. I'm just trying to learn the trend in the noisy data, right? So what we use as an input here, where is it? Yeah. So the input that's going into the neural network, this input is is a collection of the 2-point functions that are made into loops. And we first did it when we wrote our quantum loop topology paper first in, I guess, 2017. When we did that, it was kind of, you know, a set of accidental decisions that turned out to be right. We didn't quite know why it was a good decision, but it worked, so we were happy. We published it. But after the fact, that as we further worked on that, what we learned was decision of using loops were helping us retain gauge invariant information. So that was a good decision if we want to go after anything that is, you know, physical. So what we do is we collect for a given site, let's say here. So this given site, it has neighboring sites. With its, for given this one site, I have used all the use the neighboring sites to make a loop, and each line of my triangle. And for transport, we also use quadrilateral loops, triangular and quadrilateral loops. Each of these is the sides are the 2-point functions evaluated at a single Monte Carlo instance, and we collect them to form a loop. And now for this side, for the shortest loop, I have 4 of them for triangles, and I would have quite a few more quadrilateral loops, and those go in as input. And what we do is we take those inputs at somewhere deep in the phase. So in this case, this is the phase diagram of the spin fermion model with spin density wave fluctuations coupled to fermions. We are walking down this temperature axis. So we do training at deep in the superconducting phase, training at, you know, way up in the normal phase, and those were, say, 2 training points. And once the neural network is trained, we fix the network parameters, and we give this quantum loop topography data for the rest of the phase space. And we find the output to go from the metallic state to the superconducting state over this range of crossover, which is consistent with the superconducting fluctuation. And then we were able to discern, you know, why would this work? At least when we look at a mean field model of a superconducting transition, because in mean field model, everything is quadratic. We can actually work out, there's no vertex correction, no anything. We can actually work out what the conductivity is. And we can see that the inputs that we used would enter in that explicit expression for conductivity, which gives us physical intuition and plausibility for why using such inputs would have been the right kind of thing to be able to detect the difference between some sort of measure of transport in a superconducting state and some sort of measure of transport in a metallic state. The reason why I say transport is because of that insight that I have. I know I can use this input that I have used in this model in a simpler model, such as a gap mean field superconductor, to actually, if I use not noisy but expectation values out of them, I would get Kubo formula. Right? I would get the transport information. I would get conductivity. So if I use a noisy version of those, and the real system would not be a mean field superconductor. In this case, it's not a mean field superconductor. But there will be other noise, and I would probably have to combine those input to form some more complex function. But neural network does form complex functions out of my input, because it forms these nonlinear functions. I said neural network is just writing a function. So if there was a much more complex function that I have to make out of my 2-point functions to capture the transport, it would form that more complex function. So this is what's on this preprint learning superconducting fluctuation regime here. And when we use the negative U Hubbard model and do the mean field theory, compare the mean field theory and a negative U Hubbard model to this using machine learning, we found that the machine learning detected the onset of superfluid density, essentially starting to detect the superconducting fluctuations. Now what we are doing that right now I've taken on an undergraduate student for the first time. I haven't worked with undergraduates before, but undergraduates these days take computer science courses, and he's a double major, so he knew all the kind of machinery side of machine learning. And our fellow Sam Lederer and this undergraduate student, we're working together on Sam's data on nematic fluctuations, and we're finding the non-Fermi liquid regime and the metallic regime to be distinguishable by the neural network. And so now we're going to try to extend this to see whether we can get like nematic metal, non-Fermi liquid state, and a Fermi liquid metal to come out to be different. And it's not as quantitative as Maxent or any other analytic continuation, but it's giving us sort of a snapshot of what's going on. And in a way, it is not biased by the scheme of analytic continuation.
More questions? Yes, Philip.
So I wanted to come back to the diversification you had on the SCM data, where you sort of put in different types of disorder. And I guess my sort of two, in a sense, related question is, one is, do you put in sort of disorder from the physical model, where you have some estimate of the density or the temperature or fluctuation you expect, or vice versa, can you extract kind of what type of noise you have from your learning?
Right. So let's see. Where's my mouse? So this is a training set generation. We're not using any kind of, so to use temperature, and there are other sources of fluctuation. So this is like low temperature data for Kelvin. Presumably there is some quantum fluctuation, and it's a complicated system. So I don't have microscopic model for this disorder. What I have is a phenomenological model for the disorder, guided by what is the physics of charge density waves. We know charge density waves are described by complex order parameter. We know complex order parameters can have amplitude noise and the phase noise. We know charge density waves as a complex order parameter can have vortices, topological defects. So we know these things exist. These things are allowed. So we are allowing for all sorts of fluctuations that we know from theory that are allowed, guided by the experimental data in terms of the degree of those fluctuations. So we put in enough amplitude fluctuation, enough phase fluctuation, and enough topological defects to capture the degree of disorder in the experiment, but we don't have a model to get to those disorder. So we don't know what's necessary to get them.
Sure, but just very on the technical question, the numbers you put in are those extracted from the data?
Yes. Extracted from the data in the sense that we put in enough disorder to say broaden the. So this is cosine function, right? If I didn't broaden anything, I'll get a 1 peak and 1 Q. So putting the phase disorder and amplitude disorder will broaden this function, broaden this distribution, and putting the topological defects would also further broaden this function. And we know the number of topological defects because we can look at the pattern, and we can actually count how many topological defects we have. So roughly, we know we have somewhere around like 20 topological defects in the data. So these kind of observations we have about the data is guiding this model. This kind of the training set model we have, this looks pretty far from actual measured data set. So there is a question of, can we trust this generalization going from the models that it's been trained on to the real data, which is much more complex. And so one thing that we're working on right now is using what's called generative adversarial network, which is there are two neural networks. One is trying to make what you have as close as possible for the target data, and the other is trying to discern, and there's a competition between these two networks. And we're trying to see whether we can use this generative adversarial network GAN setting, starting from different hypotheses, let each of the training set associated with each of the hypotheses, let them evolve, try to let them get as close as possible to the real data, and see if we can use that as a way of, discerning, who was a good starting point to get to the data.
Okay, so let's thank Eun-Ah again.